Thank you for welcoming me in your community. In fact, I'm not a specialist in this domain. I hope to become one soon. It's not my prime area of specialty. And I think in that domain, if I want to learn, the best thing is to start presenting your work. So that's the idea of this talk. I hope it will be of interest to you. It's about Internet of Things, which is a very trendy topic. And I will explain what I've done in this domain. And my talk will be in two parts. The first one will explain why I get into that area. And the second one will go further, and perhaps with foolish idea, you'll tell me if it is reasonable or not. I've learned that processes are cheap in Erlang, so I'm very fond of processing, and we'll see what we can do with that. So I've been working recently for an internet service provider located in Marseille. So that's the reason why I went into this field. It is a very promising company based in south of France. I'm coming from Marseille. You can see, well, you got some parts of the harbor behind the new building. So this is a new headquarters for the company, which is growing quickly. And so it has its own data center located there. And with this new building, the idea was to have a flagship building. So it needed to be both smart and green. So green, everybody knows what it means. You need to be energy efficient. But to be energy efficient, you need to be smart. And there are a lot of regulations which are now being enforced in order to ask builders to have very efficient buildings. But I want to explain you what is a smart building first. So this is the building we were, when I arrived, the plans were already made, and so the data center is very close to it. But it's a very nice building. You see on the rooftop there are solar panels. So it's what we say and energy efficient. It's énergie positive in French, which means that it produces energy, but it's not really positive in the sense that it produces only a small part of the energy consumed by the building. So it's only during the weekend that, in fact, that the ratio and the difference is positive. Okay, so it's a bit misleading, and I've been a bit disappointed in that area of green buildings by learning those things. So what does it mean for a building to be smart? So buildings are quite complex systems, and in order to have some comfort in the building, you need to heat it, you need to have air conditioning, you need, especially in Marseille, that's maybe the main difference between Stockholm and Marseille. The consumption in summer is the most part is due to air conditioning, whereas I imagine that in winter the cost of heating buildings in Sweden, if they are not well protected, is much higher. So, but we've got the Mistral wind, we'll see that. So you've got a system for heating, for ventilation, for cooling, for lighting, for many things, and you have to manage all these systems. So the key term is HVAC for the people who are specialists of that field, and it's quite complex management problem. Of course, if you think of your house, you've got some regulators for room control, but it's a small problem with one room, whereas in buildings you've got many rooms, many offices in fact, and you have to regulate the whole thing. So it works anyway, because we don't need to have an optimal regulation for a building to be usable. But if we can optimize the way we manage the building, that's of importance. And here comes IoT, or the idea of collecting information from the systems in order to be able to have a global view of what is happening, and to better learn on how the building is working, and how we could use the different options we have in hand in order to manage it better. And this could result in lower costs or better for the people within the building, right? So the emphasis was on the building management system. The boss of the company had already developed within the team around me the building management system for the data center, because that was an industrial system where you can collect also lots of information about cooling, which is really important for cloud data centers. And so the idea was for this new building, which is a very well, it's a vitrine. The company is member of the French technologies, younger companies. So this, I said, is a flagship building. It was important to demonstrate that things could be done which were at least state of the art. So that was the context of this work. And we had the plans, the floors, the offices, open plan offices, and how can you control that? Well, in fact, we're not going to reinvent the wheel. We are going to use equipments that are on the market. And when we have a look at the equipments which enable you to control the temperature, the cooling, the ventilation, all these issues, you have a lot of well-proven technologies. But from the point of view of a computer scientist, these are all dated technologies. It's a bit weird. I mean, we are from a different world. This is electrical engineering. It's mainly put in place by electricians. And we have a view from IT, which is a bit different. Okay? But nevertheless, it works. And for instance, so we choose a standard which is KNX, which is a standard of European origin, which enables to perform building automation. What does it mean? So you've got certain devices. Some are smart, which means they can push data upstream to a supervision center, or some are not really smart, but they are controlled by a smart device which can get, for instance, the temperature using a simple wire, and then be able to communicate to other systems by using communication channels. Right? So here you've got a small drawing showing that the lights can be handled by the DALI protocol, which is a companion standard with KNX. And you've got the heating. You can also have access control. You've got cooling. You've got ventilation, because you have to change to renew the air in the ducts. And if there are many people in the room, of course, you need to have fresh air. And all these make a lot of equipments, and you really have a lot of systems to control. So that is the way the buildings are automated nowadays. So you've got a lot of devices which are controlled by local controllers, which transmit the data further up to a supervision, and the manager has the information on his PC from the supervision level. The idea we had was to have a cloud-based building management system because we had the data center around the corner, so it was easy to store everything that we can collect from the building and maybe for later use for data analytics. But that was easy to do, so we've done it like this. So in this talk, I'm going to take a different view. So we'll see if it is reasonable to do that or not, if there are alternatives. But to go back to what is done in practice, so these are industrial Internet of Things systems. So why am I calling them Internet of Things? Because in fact this has been existing for a long time. These are called SCADA system, so data acquisition here, and the system control, supervision, control, and data acquisition. So you've got the 2 points. And that will be important to distinguish, because data acquisition means I want to collect data, and if I'm a manager, I'm the top of the pyramid. So you've got different systems in the company. Here you've got the ERP for the global management of the company, and you've got different layers, and that's the way it's done in practice in industry. So we didn't want to throw all this all away, and so we had to stick to the lower layer, which are field proven. For instance, if you have measurements, you've got wires and they can stand long distances within complex buildings without being noised, and that works. So the management sits on a different layer. So the bottom layers are being held by traditional equipment. They measure and they can throw some alerts. The control, there's some local control for the equipment which are not connected. And they, for instance, you've got a regulator in a room to control temperature. That's something common. But you have got very many in our building. We've got, for instance, 200 regulators for all the offices, which are open space. And on top of that, you want to inform, to archive, to analyze, and to decide. That's the management task, and that's the task of the building management. So these are different terms. Data acquisition going from the bottom to the top, but supervision control is the opposite. You've got, in fact, it's called also instrumentation and control in industrial system. When you've got an industrial process to supervise, you've got the same type of installation. Okay, but nowadays the term industrial Internet of Things is about the same. But the important thing to remember, it's done in a hierarchical way. So as I said, there are two worlds which are speaking different languages and which do not have the same views of the world. So there's the bottom level, the domain of electricians, let's say, and the top level for management. We are used to web services, and web services we can just ask a request and get a response, and that flows naturally. But that's not the way, for instance, KNX standard works. But what's nice is that KNX standard has its own field bus, which controls all the lower devices, and at some point, all these networks can be coupled to an IP coupler. And from that point, all the information that you get up are information that you can control from within IP. So that's a nice point for us, because we just need to know what is addressed on the bus here. And the rest is being done locally by the automata. We don't have to interfere with that. So in order to control and command the system, we just need to get the information coming up, and also be able to send some commands down to the devices which are, for instance, temperature sensor is a sensor, and a valve is an actuator. So you've got plenty of these in the systems. So up to this point, what we have is the information which transits within the local field bus is being encapsulated within IP frames, and we get everything within a world that we know better as computer scientists. Okay, so if you want to listen what is exchanged on the bus, you just have to connect to these routers. You open a socket and you can listen to it. The nice thing about KNX, and this is a good match with Erlang, is that it is an event-based protocol. So devices speak regularly. They talk to everybody. In fact, it corresponds to multicast in IP. And so everybody hears what's happening on the bus, and if it is of interest to you, the device is programmed to take the data and interpret the order and act in response. So that's the way it works, and regularly you've got information coming in, and you don't have to poll the devices, which is very important not to overload the network. So you've got everything coming in, so you open your UDP socket. It's the traditional way. So you see that you can accept some loss of data, but normally there's no much problem. You need to know also that the throughput of these field buses are quite low compared to usual throughput of IP. It's about 1,000 times lower. It's the old modem baud rate. Okay, so in fact, if you just use your Gen UDP library in Erlang, that's all done. Well, the difficult thing is to get some proper parameters, but then you receive a stream of messages. Of course, they are KNX messages, but they are encapsulated within UDP, and you can try decoding all this stuff to understand what's going on. And the specification is open. You can try it. It's a lot of pages, but fortunately, it's well done. There's some German explanation in it, in the diagrams, but never mind. It's a mixture of different influences within European engineers. Okay, so you're done, but only for the bottom-up part. What's happening is the KNX protocol has a way which I say is different from the web services. You write when you write to a device. In fact you can, if you want to light on all the lights in this room, you can light one light individually or the group of lights. So you talk to a group address usually, which can be one or many, and then you send a message, which is a command for lighting on or off, and you will see all these writes being written on the different pieces of data that you've got on your flow. On the other hand, you cannot query the data. If you want to ask what is the temperature of your room at this particular office in the building, then you have to send a read command, and the read command will have to wait for a response coming on the bus. So there's no server if you want, and you will have to wait on the bus what's going on. And that's why it doesn't work for sending requests. So it works fine for getting the information which is naturally written to the bus. But if you want to have specific information, for instance, for polling, but as I said, it's by far the majority of the information comes upstream. But if you want to do the other way, you have to send some information, and for doing so efficiently, you need to do two things. So first, you issue your read value telegram within a data frame, and then you will have to wait for a write value, a response. So just to explain, this is the socket which is open. It received data. Here I put a middle point, which is here to dispatch information, and I need to know if I want to, for instance, that's a solution I've devised. If you want to send some information and ask for a query, get that value. So I write read me the value for that device or for that group of device, and I need to memorize that I've sent a read somewhere. So that's the purpose of that actor. And then I have to wait for the response. So I have to wait so that is the sending information to the KNX bus here, which manage, and the equipments are autonomous. And the response will come sometime afterwards, here on this way up as a response from the system. So the majority of information are write telegrams, but there are some response telegram which will appear from time to time, and that will be the role of this agent to give back the information to this agent, which I said is transient because it's a blocking read. It's kind of RPC call, right? So that's a way you can deal with having a kind of web services within your system. You ask a request, you get a response, and with a few lines of code, you've got a working system. Okay, so I think this is up to what is being done by industry. At least I think we didn't find solution. This is a prototype provided by the KNX Association, which tries to promote web services for KNX. So this is not yet industrialized, and we need to have some system which works fine and which can work on also on the Raspberry Pi. This is a demonstration which is available on Raspberry Pi too. Okay, just with a few lines of Erlang, you've got the solution to that problem. So let me explain just before concluding that first part what is the information we have in hand in order to be able to do all that information decoding or encoding in the other way. So we've got a system to configure all these devices implemented by or put in place by electricians. This is the software ETS, which works only on Windows systems, but never mind, it's being used by electricians to configure your system. So that's why the devices know how to respond to different messages. You can program them with blocks with their in fact it's the way they have to automate the system. So you've got, in fact, a PC with all this configuration files, and you can extract from those configuration information the information for decoding the messages, because you know that at some point that group of devices will be, for instance, lamps, and for lamps you've got specific data points, and for decoding those specific data points you need to have that information. And then you go down to the standard, which is, well, as I said, they were trying to pack information in a few number of bytes, which seems all dated to me, but then it's a nightmare for translating. But with the help of the bit strings, it simplifies things a lot. So the important point is that we need to have some knowledge base within your system in order to be able to translate and to decode information. So this is distributed within the nodes in the solution explained here. Okay? So, and we've done. We've got a basic system which enables us to get information and to command if we need the system. So, what can we do after that? If you listen to what's happening on the bus, this is what you get. You've got the timestamp, you've got the event on the bus, you've got the address, which is the physical address. So the events are written from a physical device to a group of devices. You've got two different types of addresses, who speaks to whom. And these are the group device, as mentioned, for the group of lamps, for instance. And these are the most important concepts in KNX. And these are the different devices which are connected. And you see that you've got a lot of information. For instance, if you want to have an optimized building, you want to shut down lights if it is not needed, if you've got enough light from the outside. So you've got, for instance, device which measure the ambient light and which will switch off the artificial light if it is not needed. And there are some tiny rules which say that, to be even more precise, if there is nobody in the room, in the office, and if there is not enough light, you don't need to light it on anyway, because there's nobody. And this saves money. But it's adds complexity, that's why we need some automation at the low level, but it saves a lot of money, and it is going to be enforced by regulations. But if you run this for one day, for instance, this is the PDF output, and what you get is 24,000 pages of information. It's not big data. It's, if you measure, you've got about, in our building, which is a 4-story building, it's about 10 telegrams per second. It's not a lot. But at the end of the day, it's a lot. So what happens if you don't have a data center nearby? So this is a not very good view. This is north of Marseille. This is the data center. You've got a roundabout here. You've got the exit from the motorway. and you've got the new building here. Okay, it's just you cross the corner and you've got it. So my colleagues are system engineers. So we wanted to have a building built very quickly. So let's stick to proven technologies. Let's move all the information into the data center. We've got plenty of space. We've got fiber optics connections, so it's no problem. We can collect all this data and exploit it in data center. So I wanted to. I'm a researcher, so I wanted to think a bit differently. So what do we need exactly? We need to have in order to have good management, we need to have a proper representation of reality, and we don't need to have too many informations. So the data, more data, is not necessarily better. Less data could be better. So we want to avoid infobesity, and for the people in charge of the management, you've got some mental overload if you've got too much information. So all this together says that we should try to do things in order to avoid sending data that we don't know what to do later on. So that was the principle I wanted to apply. And in the case of building management, what you measure are typically temperature metrics. So what you have at the end of the day is a time series, and you're dealing with many time series. But in order to make things clear, I'm choosing information from my favorite windsurfing spot. Here is, in French, what you get. This is the information at every interval of 5 minutes interval. With the wind, especially it's the wind and direction of the wind, which is important for surfing. And this is the past hours. And in fact, if you want to compare to what's happening in big data environments and architectures, this is an image which has been compiled. This is the batch view. And this is renewed, refreshed regularly, and this is the real-time view. So you've got the two views in your system for data acquisition. But at the end of the day, what matters is presumably this. You've got information about the force of the wind and its direction. And this is a much nicer representation because you've got the actual value and the mean value, and also this means that you've got a very gusty wind here. And depending on your level, you will decide what to do. So what can we do with data from that? So we've got the real world, which has data to send us. And in the virtual world, we want to have a view of that real world. So we've got a building information system, but we've got devices. We can have a model in front of it. We've got the data points which are connected to the field bus, and this can be represented by software objects, and the thing can be represented by a twin. So these are the correspondences between the virtual world that we want to manage and the real world. So I'm going to be within the virtual world and to ask what can be the purposes of that twin. What could we do? So this is just a reference to the Lambda architecture for big data. We don't want to lose any data, and you've got a master data set which is stored somewhere, and because it takes time to produce the batch view, you've got a real-time view in parallel. But that's clearly a cloud computing view, where you want to collect data before transforming it. You don't know what's going. In the fog computing view, you try to have some processing more happening anywhere on the path up to the cloud. So you've got the device at the bottom, and I will be interested only by the upcoming streams. So in that idea, I think that if you force you to think of what you want to do with your data before collecting it, that can be a way of saving bandwidth, saving latency, and also having something working more locally on smaller devices. So coming from raw data to refined data, this is an image of the pyramid we had before, and I think that can match also with what's happening in industry. So you want to reduce, to consolidate your views, to reduce information, to have more valuable information, and at the same time, when you go up the pyramid, you reduce the pace at which you produce information, and that allows you at the bottom level to have a horizontal scalability, and the top level you will have possibility for vertical scalability. Okay, so these are the properties of the case I was introducing to you, which are moderate data, and so that's why I can play with it and try strange things for going upstreams with that data. So we'll concentrate on the upstream view, and we start from a source node with that information as the datagram we've seen before. You can decode, timestamp, dispatch the information, and then if you here, once you've decoded, you partially decoded, then fully decoded it, you've got the data which is of interest to you for the precise time at which it arrives. And then you can try to have a high-level view by adding more processing later on, but you're still working on the flow. So that's the idea, which in fact means that you're transforming your view into a data processing flow. You've got your workflow, you refine it this way, and this can lead to interesting architectures. So what I want to just introduce is the way I've started to experiment, because this is an ongoing work. So I'm defining functional blocks, which are in fact second-order function because they are applying a functional pattern on data on the stream. You repeat it, that pattern, and then you perform some computation on the flow without blocking the flow, and that can be done in parallel with all the streams going up to the top of the pyramid. And you can also ask these agents to store data in memory or on disk. You can give parameters for retention policies in order to have a limited form of failure handling. Okay, so I'll give you an example. So maybe I show one simple example, go back to it later. So this is, you've got your data point, the twin which gets the precise information at time t for the value v, and you can compute the maximum of the period you've stored in memory, the average and the minimum. That corresponds to the diagram we've seen before and associates with maximum, minimum and mean value to have the higher level view this way. So what you do in fact is you define a graphical specification, and out of this graphical specification you will produce registered processes, and you can automatically produce code generation. Well, for the time being it's semi-automatic. And it's different from pub/sub because you've got a direct consumer producer to consumer connection, right? And that can be placed on various Erlang VMs. I could say nodes, but they are nodes which are different meaning. And in order to run it, you just have to open the tap, and the flow streams to the source, and then it feeds all the processes, and you get the results. So this is a final illustration to get a grasp of that. I take a time series with just one value, and the time is the abscissa. And here, well, I'm cheating. I'm producing the regression, the linear regression curve. But you've got the minimum and maximum, which are fluctuating, and you will see that depending on the size of your window, what can happen if you've got a smaller window, your minimum will go up, so you have to adapt it. This is a statistical function used naturally, which is the smoothing of function with a moving average. You've got your sliding windows and you apply a moving average. I'm using it just for demonstration purposes because it's nice to way of showing operator composition. If you have got two moving average operators, you combine them. What you end up is a triangular moving average, which gives you a form factor, which is, for instance, if I've got three items for my time window, if I combine two successive average operation, I will have an average with weights which are 1 for the first, so it will be of size 5, 1 for the first element of the list, 2 for the second, 3 for the third, and then 2 and 1. So that's why it's called triangular. And you can try as an exercise with this type of modeling that if you chain two simple moving average filter, you've got exactly the same result as a triangular moving average filter. Okay, and here, just by doing so, just for one feed, you've got already 8 processes involved, and depending if you want to really to maximize parallelism, you can have more in order to avoid locking, etc. So you see that if you want to generalize this, it will end up with lots of processes. And the more processes you have, the more difficult it will be to manage. So that's a question I didn't answer yet. But if you want to summarize, because we've seen the Lambda architecture, the people from Kafka have refined it as the Kappa architecture. So if I'm a bit blunt, I would say this could be the Delta architecture, because it has the shape of the pyramid. So it's really experimental, but it makes distributed processing, stream processing, real soft real-time stream processing, with some kind of round-robin storage capabilities. It can be used for monitoring and control, and what's important is that you got these layer views. Okay, so once you've got the proper information at hand, you can choose what to do. So this is not me. Huh? Thank you.